Hello guys and welcome to a new IB IGCSE chemistry video tutorial series. So I'm going to start doing this on my channel because I feel that chemistry is another important subject out there that a lot of students need help on. So we're going to start off today with the lesson 1, and I'm going to be posting video tutorials based on chemistry in the coming time. So if you do have any specific requirements you'd like to know on any aspect of chemistry, do let me know. Particularly, I'm basing this on the general topics of chemistry, including stoichiochemistry, and we're going to be doing practical works and tasks so that you can understand better. All of the PowerPoint slides I'm going to be creating for chemistry is originally created by me, so we're starting with this one for lesson 1. So if you'd like any PowerPoint slides for any lesson, just let me know in the comments section down below, and then I'll do my best to upload it on an open drive so that you guys can have access to it. So for this lesson 1, we're going to be learning how to derive chemical formulas, how to balance chemical equations, how to interpret word equations into chemical equations. One thing I would like to advise you guys to always have and to just make sure you get a copy of is the periodic table. It does kind of tend to differ across different examples, but it's basically general. You would normally see, of course, the elements, and you'd see the groups that are stated, as well as the atomic mass and the ionic charges. But it's always good to have a copy of the periodic table, and because especially for today, we're going to kind of be referring back to this back and forth since we're learning how to do derivation of chemical formulas and how to basically balance equations and interpret word equations into chemical equations. Another thing I would advise you guys to get is this periodic table with the polyatomic ions, and this basically shows you the different polyatomic ions and their ionic charges. So it's also important. It also shows you the different elements of the periodic table. So if you could get one complete one like this, where you had the elements of the periodic table with their charges, their atomic masses, and you also have a periodic table or a table that shows you the polyatomic ions, like what you can see on my screen here, that will be very useful across what you do in chemistry, especially when you deal with chemical formulas or balancing chemical equations. All right, guys, let's get started. So the first thing we're going to be looking at is cations and anions. We're going to be looking at the difference between the cations and the anions, both the positive and negative charges. So first things first, I'm going to go to the next slide. Here it says, what are cations and anions? So an anion is an ion that has gained one or more electrons, and this has made it to acquire a negative charge. So whenever you see a negative ionic charge on an element, that basically is an anion. When you see a positive charge, that will be a cation. So it's the opposite. You kind of look at this in the opposite way, where you actually have a negative charge, but it's actually gaining one or more electrons, and you have a positive charge, but it's actually losing one or more electrons. So positive charges are considered as cations, and negative charges are considered as anions. Okay, so I just underlined a particular question from these series of questions. You can try these questions out on your own for practice as well. But we're going to look at question 7. It says calcium carbonate is a critical component of the shells of the various aquatic species. Identify the cation and the anion in the calcium carbonate. So this is the reason why I asked you in the first place to have a polyatomic periodic table, because it is essential to look for charges for what you need in terms of elements or polyatomic ions. So calcium carbonate, the first thing you need to do is when you have a word statements like calcium carbonate, you definitely know that it's involving calcium, but it's also involved in the polyatomic ion of carbonate. And we're going to be seeing what polyatomic and monoatomic ion means if you are not aware. But basically the difference between a polyatomic ion like a monoatomic ion, like calcium, and a polyatomic ion like carbonate is that the monoatomic ion contains only one atom, but a polyatomic ion contains more than one atom. So that's really the difference between the two. So this one contains more than one. So I'm just going to say greater than one atom. Okay, guys? So now how do we derive this chemical formula when they've told you that calcium carbonate is an important part of the shells of aquatic species? Well, what you need to do to derive a chemical formula is go back and look at the ionic charges. The ionic charge for calcium is going to be +2, as you guys can see here on my screen where my mouse moves. And then you're going to look for the polyatomic ion of carbonate, and carbonate is a 2-. So basically, if you have a +2 here, you could just say +2. And if you have a -2 here for the charges, one way you could derive the chemical formulas is by basically exchanging these charges, these ionic charges, to become subscripts. Subscripts are the numbers that you find below the chemical name of a particular element or compound. So if you exchange these ionic charges, so you bring 2 plus 2 all the way to carbonate, and then minus 2 goes all the way to calcium, you now see that the charges are going to be plus 2 minus 2. So if you take them as plus 2 minus 2, obviously that's going to give you a 0. So it means eventually no one of them is going to have any charge or anything, because it's always important to take note of the charge. If it's a plus, for example, 3 minus 3, that's always going to give you a 0. Anytime the charges are the same, but like the ions, are the same, but the charges are different, and especially where you have plus and minus, it always equals to a 0. So the chemical formula in this case, calcium carbonate, is going to be CaCO3. So this is how you're going to write it down. So moving on, guys, to the next thing, we're going to move on from what we've seen right now in terms of calcium carbonate being an important, a critical component of shells of the aquatic species. We're going to now move on to look at the next aspect, which in this case is going to be, what is the difference between monoatomic and polyatomic ions? So guys, monoatomic ions, as I've said, basically consist of one atom. So it's usually just single elements like bromide, as you can see here, or like iodide, oxide, sulfide, fluoride, etc., etc. So any one of those elements that consists only of one atom is considered monoatomic. Polyatomic, on the other hand, is basically consisting of more than one atom. So as you can see here, so like what we have carbonate, as we've seen, it has actually 3. The number subscript is 3. And so that it is not just one single atom. You have one atom of carbon and then oxygen, so that's about 2. So it consists of more than one atom. So there are basically 3 atoms of this calcium carbonate. So always remember, when it's more than one atom, then it's not considered as monoatomic, it's polyatomic. Always remember that if there's a number at the back here, for example, if there's a number, you can generalize this whole thing by saying 2 molecules of. So that's another thing. But if you wanted to say atoms, you're going to say 6 atoms, for example, of oxygen in this case. So please let us not be confused. If you have carbonates like that, basically you have 1 atom of carbon, and then of course for oxygen you have 3 atoms of oxygen. So this subscript number is used to represent the number of atoms that is for the element next to it. So don't confuse it with that of carbon, because carbon is single-handed. There's nothing near. If you had something like this, which is another example, then it means you have 2 atoms of carbon in that situation. So it's always important to identify how you know the number of atoms and how you can consider molecules. Molecules would just basically be the number that you have behind the chemical formula that represents the entire elements contained in that chemical formula. So this is also considered as a number that you find below a chemical an element is called a subscript. So I'm just going to write it here. So always remember, a subscript is a number right below a chemical element. Okay, subscript. Now, moving on, so polyatomic ions are basically containing more than one atom, even if these are of the same element. So again, like I said, if you see this atom is carbonate and you see that it's 3, the subscript number is 3, so this is subscript, but it shows that there's more than one atom because there are 3 atoms of oxygen and there's 1 atom of carbon, so a total of 4 atoms in this chemical compound. Now, moving on from this, so they give you some examples of monoatomic ions like calcium, which has an ionic charge of +2 or 2+, or a polyatomic ion like carbonate, which has a charge of -2 or 2-, and then, of course, other polyatomic ions like we can see here, ammonium sulfate, etc. Now, the differences between cations and anions is that a cation is an atom or a group of atoms that bear 1 or more positive electric charges, whereas an anion is a group of atoms that bears 1 or more negative charges. So always remember, cations are positive, anions are negative. If you were to identify the cation and the anion in this chemical compound of calcium carbonate, of course, calcium is going to be what? The cation. And then carbonate, which is gonna have 2-, is gonna be the anion. So always remember, anions are the ones that contain the negative charges, cations are the ones with the positive charges. So the electric charge for cations is that they carry one or more positive charges, while anions carry one or more negative charges. The atoms, cations, are formed from metal atoms. Anions are usually non-metal atoms. The electric charges is that cations are attracted towards the negative terminal, obviously because they're positive, so they attract to negative. And then the anions is the opposite, which attracts to the positive terminal. So now, guys, we're going to be looking at how we can derive chemical formulas. One important thing is to always refer to the groups of where these chemical elements belong to, and what is the general charge for those elements that are found in those groups. So, for example, in group 1, the normal charge would be +1. In group 2, it's +2. Group 3 is +3. Group 4 do not contain a charge. Group 5 is -3. Group 6 is -2. And group 7 is -1. And then that's 0. So this is essential, that can help guide you to understand, at least for the elements, what exactly their charges are going to be. And so that's easy for you to use to derive the chemical formulas. For example, lithium belongs to group 1, hence it's going to take a charge of +1 or just plus. So if you wanted to combine lithium and chloride together, then basically chloride belongs to a charge of group 7, to the group of group 7. And group 7 have a charge of -1. So if you put the charges above the elements and you exchange them, they become subscripts of these elements. So subscripts means the number at the bottom. And so we have 1, 1. So by convention in chemistry, that is by standards, you don't need to necessarily write the ones. You just write it at lithium chloride. So that's pretty much how to find those the steps to go about deriving chemical formulas. Another example is here with magnesium chloride. Magnesium belongs to group 2, so it takes a charge of +2. And then chloride, of course, it belongs again to group 7. So that means when you exchange these subscripts, it becomes magnesium takes the charge of chloride or chlorine. And then, of course, chloride takes the charge of magnesium. So eventually, you don't write the 1 again, like I said, by convention. You will get the chemical formula of MgCl2+. And the same thing applies to magnesium oxide. Now you can see that this chemical formula, because just like what we saw with calcium carbonate, they both have the same charges. So if you actually say 2 plus 2 minus, you're going to get 0. But if you could also do it in a way where you simplify the 2's, and then that gives you 1, because 2 divided by 2 is 1. So eventually, you're not going to be writing the 2's out because they cancel out. So the formula will just be MgO. And so this is another example of how to write chemical formulas for when you have these Roman numerals. These Roman numerals are very useful to tell you the charge of the element that is on the left side. So for example, guys, you see iron 2 chloride. So that iron 2, the 2 is actually telling you the charge of iron, since it comes in iron 2 or 3, is actually a +2. So they're saying it's the +2 one, since it has more than one ionic charge. So this is iron, which has an ionic charge of +2, and chloride has a charge, of course, of -1. And so if we exchange the subscript number, again, you will see that chloride takes the charge of 2 and then iron 1. So by convention, we don't write the 1. Eventually, you get the chemical formula of FeCl2. And the same thing goes for sodium nitrate. The only difference is here you have sodium as a monoatomic ion and nitrate as a polyatomic ion, because it has more than 1 atoms of oxygen plus 1 atom of nitrogen. So again, to be able to derive the chemical formula, if you exchange these charges of this monoatomic ion and polyatomic ion, and remember, if you want to find out the polyatomic ion of nitrate, if we go back to the polyatomic table and we zoom it in, we can see that the polyatomic ionic charge of nitrate is going to be minus. Okay, so as we can see here, not nitrite, but nitrate. So that's pretty much how we derive. It's easier this way. Over time, you get used to these charges and you kind of remember them. So you don't necessarily have to be going back and forth to find what they are. So the polyatomic ion of nitrate has -1. So again, it's the same thing even with this kind of this kind of chemical name. So to derive the chemical formula, it's the same thing. You put the charges again at the top. Sodium has +1, and then nitrate has -1. When you exchange these numbers to subscripts, they become 1. Each of them takes the 1 charge, and by convention, we don't write it, so it becomes NaNO3. And so on, guys. So these are more examples. I'm just going to allow you to go through this for now. And as you can see, this also contains some common polyatomic ions that we normally use mostly in chemical formulas, and some examples of transition metals and your oxidation states. So I'm going to move on so we can do an example. So here it says, write the chemical formula of the following: strontium fluoride. So let's take it in a new slide. Let's do it together. So strontium fluoride tells you that you need to go find the ionic charge of strontium and the ionic charge of fluoride. So that's the first thing you need to do when you're trying to derive chemical formulas. So let's go back to the polyatomic table, periodic table. So if we look for strontium, you see that the strontium, let's just find it. It's Sr. There it is on this side, guys. It's on the left side. So strontium has an ionic charge of +2 or 2+. So let's write it down. So the chemical formula is Sr and its charge is 2+. So that's for strontium. Now for fluoride, of course, fluorine, which is a nonmetal, it has a charge of minus, that means -1. And its chemical formula is F. So you could say minus, or you could say -1. So what you're going to do, as we know with the steps of how to derive chemical formulas, is you're going to be exchanging these ionic charges as subscript values. So this one goes for strontium, this one goes for fluoride. So once you exchange it, eventually strontium is going to take the charge of 1, and then fluoride is going to take the charge of 2. So by convention, you don't write this 1, it will just be written as SrF2. Okay, guys? So this is the chemical formula for strontium fluoride. So that's how you really derive it. So let's look at the next example. The next example says that we need to also find the chemical formula for, so let's go down. So we're going to be looking for the chemical formula for nickel 2 perchlorate. So I like this because it does combine all of what we've seen just now. You notice that it does contain this Roman numeral. So we're going to have to say that nickel, since it takes more than one ionic charge, what they're referring to in this chemical name is the 2+ ionic charge of nickel. So we're going to write it down. So we need to find the ionic, so we make sure we find the ionic charges for nickel to be right, and also for perchlorate, which is a polyatomic ion. So let's look for nickel first. So nickel is over here. As you guys can see, it has a +2 and a +3 charge. And perchlorate, as you guys can see at the top here, has a Cl04- charge. So what we're going to do is we're going to go back and we'll write out nickel with its chemical formula. So it's Ni. And since the Roman numerals, so the Roman numerals actually help to tell you what kind of exact charge that they want you to use for this chemical name. And as we can see that they're referring to nickel 2, so it's the +2 charge or 2+ charge. So we're going to write it at the top. And perchlorate, which we already have seen as Cl04, and then of course minus. So that means now again the same step applies, is that you're going to be exchanging these ionic charges so they become subscripts. So that means that nickel takes this charge of minus or -1. So that's going to be just 1. We can write that here. And then perchlorate takes the charge of nickel, which is going to be 2. So Cl04. And then it takes the 2 charge. So we put that in parentheses, and then we put the 2 outside. So don't try to put the 2 here because it's going to be wrong. You have to put it outside of the parentheses for this chemical compound. So this is basically the chemical formula for nickel perchlorate. You can again rewrite this to not show the 1, so it's just going to be nickel, and then perchlorate, which is going to be Cl04, and then the 2, that was the subscript number for perchlorate, which was gotten from nickel, will of course come out here. So guys, you see the concept of cations and anions as well, where we said cations are usually attracted towards the negative cathode, and the anions are usually attracted towards the positive cathode. So always, it's part of something that you need to remember when you're also considering chemical formulas. All right, guys, so let's look at our next part of this. So the next part is to understand how can we balance chemical equations. So this is something that sometimes students struggle with, a tactic or a sort of strategy of how to balance any chemical equation you are challenged with. So let's take some examples from here. So we're going to take this example. Okay, so we're going to do CH4, and that reacts with, so we're going to react that with oxygen and then of course O2. and that produces CO2 and water. So this is going to produce CO2 and water. Okay? So you are giving this chemical formula and you're asked to check if this chemical formula is balanced, and if it is not balanced, you're asked to balance it. How do you do this? Well, the first thing you have to do once you're challenged with this kind of question, you're going to have to, the first strategy, the best strategy to follow is first look at the reactant side. So we're going to call this the reactant sides because this is what is reacting together. And how we know that they are reactants, we can see the positive, the plus sign that reacts them together. And then we're going to say this is the product side. And how do we know this is the products? Because we can see the arrow sign that produces that. So this sign. So we start with the reactant side. So the first step to do, guys, is to write out all of your atoms, all of the atoms of the elements on the reactant side. So that's what we're going to do now. So I'm going to erase this circle that I did to circle the charge. So let's start with carbon. Carbon has one atom. Obviously, we don't see any number as a subscript number below here or even behind here. So it means that it just has one atom. There's only one atom of carbon reacting on the reactant side. For hydrogen, we can see that it has 4 atoms, which is the subscript number. So hydrogen is equal to 4 atoms. For oxygen, we can see that it has 2 atoms, as we can see here. So that's the subscript number. And then we do the same on the product side. For carbon, we see that it has only 1 atom. For oxygen, we see that it has 2 atoms, as you can see here. And for hydrogen, 2 plus 1, because we have another one here. So don't forget to always check and see, make sure that you've counted right. So that's 2 plus 1, which is on this side that doesn't have anything, which means it's a total of 3. And then for hydrogen, we can see that it has 2. So once you've written out all of the separate elements, especially when you have compounds like this, you split them up and you write all the separate elements on the reactant side and the product side and the number of atoms they have, you can now pay attention to these number of atoms so you can determine what you need to balance so that it's balanced on both the reactant and product side. So what we see here is carbon has 1 on the reactant side, has 1 on the product, so seems balanced for now. Then we see that hydrogen has 4 on the reactant side, but has 2 on the product side. So it means something has to happen. The key is you always have to make the number of atoms on each side even so that they balance, not odd, but even. So that means if hydrogen is 4 and on the reactant side and hydrogen is 2 on the product side, what could you do so that 2 becomes 4? So obviously 4 is a multiple of 2. So it is a multiple of 2 because you can multiply 2 by 2 and you get 4. So which means that you have to put a 2 in front of this hydrogen, well, I would say in front of this water compound, but that 2 would also represent the number of atoms that you would have for hydrogen. So eventually, the total number of atoms, once you've added a 2 in front of this water compound, you've put 2 in front there, it becomes 2 molecules of water in general. But for hydrogen specifically, it becomes 4 because you have 2 now times 2, which now is equal to 4. So that makes it balanced, right? So that's balanced because we now have 4 atoms of hydrogen on the product side, which is the same as 4 atoms of hydrogen on the reactant side. So this is balanced right now, but it also changes something because you realize the number that you put behind this chemical compound does not just affect only hydrogen, but it also affects oxygen. So which also means that oxygen on this side also has 2 atoms, plus the 2 atoms that it had here on the subscript. So it's no longer plus 2, but it's no longer plus 1, but it's now plus 2. And so the total number of atoms for oxygen on the product side is now equal to 4. So that's great. It's 4 here now, but the problem is on the reactant side, the number of oxygen atoms still remains as 2. So we consider again, what can we do to these 2 number of atoms of oxygen on the reactant side so that it becomes 4? Since it's even, what we could do obviously is we could multiply 2 by 2. So that means we could add 2 atoms again of oxygen, and that will give us 4 in total. So it's balanced. So that means we add 2 here in front of oxygen. And so now the number of atoms of oxygen is 2 times 2, which is now equal to 4. So this is already a bingo because we can see that oxygen now has 4 atoms on the reactant side, and it now has 4 atoms on the product side, which basically makes it balanced. So this is also balanced for oxygen. Okay, so now when you look at the total number of atoms that you have on the reactant side, you basically look that you have 1 atom of carbon, 4 atoms of hydrogen, and 4 atoms of oxygen. And if you look again, the total number of atoms that you have on the product side, it again is the same because you have 1 atom of carbon, 4 atoms of oxygen, and 4 atoms of hydrogen. So this means that the chemical equation is now balanced to give you CH4, and then of course reacting with 2 molecules of oxygen gas, which in total is 4 atoms of oxygen. And that gives you, of course, carbon dioxide, which didn't have anything, it's normal. But of course, we have plus 2 molecules of water. So 2 H2O, which basically means 4 atoms of hydrogen and 2 atoms of oxygen. So this equation is now balanced, guys. So that's pretty much how you do a balanced equation. You always have to first write out the number of atoms you have on the reactant side and on the product side. Let's look at another example, guys. Another example is to balance C3H8 with oxygen and then to produce CO2 and water. So let's write that down. So we're going to write C3H8 reacts with oxygen and it produces carbon dioxide and also water. So again, this is pretty much the 2 parts we have of the equation. So we could write this out as this part here is what we have as the reactants area, and this is the product section. So now let's try to balance the equation. So we start with the same steps as before. Step 1 is to write out all of the atoms of all elements on the reactant side. So we start with carbon, has 3 atoms, hydrogen has 8, oxygen has 2, and then we go to the product side. Carbon here has 1, oxygen has, don't forget, 2 plus 1, which makes it 3, and then hydrogen basically has, again, 2. So we've now written down the number of atoms that is available here on the product side. So now what we're going to be looking at is, of course, we'll start with the first one. So we start with carbon first, and we see that carbon has 3 atoms on the reactants and only has 1 here. So they're not balanced. We could say that what could we do so we could change this 1 to become 3? So we could just add 3 atoms in front of carbon, and so that will be multiplied 3. And so now carbon would have 3 atoms, just as what it has on the reactant side. So it's balanced in this situation. Let's see, though, if we're going to keep it that way, because it also affects the number of atoms of oxygen. The number of atoms of oxygen now becomes, this part is 3 times the subscript number, which is 6, 3 times 2, which is 6, plus, again, 1, which is now 7. So we actually have an odd number now. Not an odd number, sorry, a prime number. So 7, all right, 7. Because we have 3 times 2, 6, plus 1 is 7. So this definitely is not going to work because oxygen is 2 here, but now it becomes 7 here. So there is no balance. We have to do something so it's actually balanced. So let's leave it for now like this, and let's look at what we could do with hydrogen. Perhaps that could change everything. So leave it as it is. Once you've done it this way and you still figure out that, oh no, but it's still not balanced, just go to the next element, because sometimes when you balance the next element in the chemical formula, you balance kind of all of them. So if we look at hydrogen, we see that on the reactant side, there are 8 atoms of hydrogen. But on the product side, we see that there are just 2. So we now say, okay, this is great because 8 is also a multiple of 2. So that means there's something we could do to 2, so we could also make it 8. So we could times it by 4. And so that means if we put 4 here behind hydrogen, or you could say behind the water compound, which again stands for hydrogen and oxygen, then it now becomes that hydrogen has 8 atoms on the product side. So that means this 4 that you've put in front of hydrogen times the subscript number, which means 8. And so it also means that oxygen now has 4 atoms of oxygen. So it no longer has 1, it's now 4. So in total, the number of oxygen atoms is 3 times 2, which is 6, plus the 4, which is now 10. So this changes, which is why I said go to the next one first and see. So hydrogen is balanced. The only problem now is oxygen. Hydrogen is balanced, carbon is balanced, now oxygen is not balanced. So here on the product side, there's 10 now, but on the reactant side, it still shows 2. So this makes it easy. Since these numbers are even numbers, we know 10 is a multiple of 2, so that means 2 what times what is going to give you 10. That will give you the key of what number should be here. So that's obviously 2 times 5, because 2 times 5 gives you 10. So which means that the number that you're going to be putting behind oxygen is going to be 5. And so guys, this chemical formula is now balanced, because you can see that you now have, as before, you now have 3 atoms of carbon and 3 atoms of carbon on the product side. You have 8 atoms of hydrogen and 8 atoms of hydrogen on the product side. And then you have 10 atoms of oxygen on the reactant side and 10 atoms of oxygen on the product side. So this tells you that your chemical formula, or not chemical formula, but chemical equation is now balanced. So it's eventually going to be C3H8 plus, sorry about my 8, plus the 5 molecules, you could say, of oxygen, sorry, not hydrogen, of oxygen, okay, from the top. And of course, that's going to give you 3 CO2, and that's going to be, of course, with 4 H2O. So this means that your chemical equation is now balanced, guys. So that's how you balance your chemical equation. So what we're going to do, first of all, is let's write the equation, and we'll do the same steps that we've done previously with the other examples. So we'll write iron, which is Fe, and then of course Cl3 plus reacting with sodium hydroxide, which is NaOH, and this is producing our iron hydroxide, FeOH3, and sodium chloride. So FeOH3, oops, sorry about my F. There it is, Fe. And then OH, and then we'll put out 3, and that's going to be also with sodium chloride. Okay, guys. So what we're going to do is to balance this equation, as we said before, step 1 is we first need to write out all of the elements and the number of atoms they have. So iron, as we can see here, basically has just 1 atom. And then chloride or chlorine, we can see, has 3 atoms. And then sodium basically has just 1. As you can see here, there's nothing, so it's equal to 1. And the same thing goes for hydroxide, which is also equal to 1. So we'll write down all of the elements and compounds, and we'll write down all of their number of atoms on the reactant side. So we'll put an R here, and this is the product side. Now on the product sides, we can see that iron also basically has only 1 atom. And we see that hydroxide basically has 3 atoms. And then we see sodium basically has 1 atom, and chloride has 1 atom. So Cl and then equal to 1. So what we notice is for iron, they actually seem balanced for now, because iron on the reactant side has 1 atom and on the product side has 1 atom. But if we look at the next one on the reactant side, which is chloride, we see that it has 3, and then on the product side it has 3. So something has to happen so that it can become, instead of 1 for chlorine on the product side, it becomes 3. So it's equal to this number. What we can do basically is multiply by 3, so which means that we're going to have to add 3 here in front of the NaCl, which represents the number of atoms of chlorine to be 3 and that of sodium to be also 3. So this eventually gives us 3 atoms of chloride. So this means that it's now balanced. Chlorine is 3 here and chlorine is 3 here. So chlorine is balanced, iron is balanced so far. Let's see sodium. Sodium also seems balanced because there's one of each atom, so sodium is also balanced. Hydroxide, however, is one on the side, but it's three on the other side. So that means hydroxide needs to also be balanced. So what we could do is to this hydroxide here, perhaps we can also put a 3, or we times it by 3 and it actually takes it to 3. So if we times 1 by 3, we get 3. And so that means we have to put 3 in front here. So that means we have 3 atoms of hydroxide and 3 atoms of sodium, which now becomes balanced because we have 3 atoms of sodium and we have 3 atoms of hydroxide. So eventually, guys, this means that the chemical equation is now balanced. So your final result is FeCl3 plus 3 NaOH gives us FeOH3 plus 3 NaCl. All right, guys, in the next one, we're going to be looking how to interpret word equations into chemical equations. And so I have a few examples here. We will do the first 3 ones, and then you can practice doing 4 and 5. So the first one is zinc plus lead 2 nitrates, and it says yield zinc nitrate and lead. So whenever you hear that keyword of yield, it means it gives. So basically, if we write this down, it's zinc, so let's write it down. It says zinc. So the key word of how to interpret word equations is just to write them step by step of how you hear it from left to right. So let's start with zinc. So zinc has a chemical formula of Zn. And then it says plus, or it reacts with lead 2 nitrate. So that means plus. We know lead 2 nitrate. Remember how we derived chemical formula? We know the formula of lead is Pb. And when we see the 2 or whatever we see in Roman numerals, it tells you the ionic charge of the element. So that means lead has plus 2 charge, since it also has plus 3. But in this case, it's a plus 2 charge. And then nitrate, which is NO3, we also have to go and make sure what the charge of this polyatomic ion is. So this is where you go back again to your polyatomic table and you try to find the charge for nitrate. So let's try to find it out here. So if we look at this polyatomic table, we can see that nitrate has a charge of minus, as you can see here. So NO3 minus. So that means, what is the chemical formula going to be? Of course, we exchange these charges. If you remember, they become subscripts. So that means eventually Pb takes this -1 charge, which we don't write by convention. And then nitrate takes this NO3 with a 2 outside as a subscript number. Okay? So guys, this means that there's going to be 6 atoms of oxygen when you times 3 by 2, and there's going to be 2 atoms of nitrogen. So now let's react this again with zinc, since we've now derived the formula. So this is lead 2 nitrate, so it's also supposed to produce for us. So let's get back to the question. It says that it's supposed to yield zinc and something else. So, oops, sorry about that. Here. So it's going to yield zinc nitrate and lead. So we already have done this. So it does yield. I'm going to have to do this again. So this word yield, because it says zinc reacting with lead 2 nitrate, and it yields zinc nitrate. Oh, sorry. So zinc nitrate, for us to be able to write down the product side, zinc we know is Zn. And we have to again find out what the polyatomic ionic charge is. So zinc is a metal. So let's scroll to this side a little bit. So we're looking at the ionic charge for zinc, and we see that it has a +2 here on number 30. So +2 is the zinc ionic charge. So if we say +2, so it's supposed to produce zinc nitrate. And we know nitrate has a charge of minus. So again, if you exchange these charges as subscript values, it becomes zinc with a -1, which we don't write, and it becomes NO3 too. So really, there is no much of a difference with the lead 2 nitrate. So this is going to be zinc nitrate, so it's actually going to be written as ZNO3 with a 2 outside, representing the number of atoms for oxygen and nitrogen. And it says it also produces lead, so Pb. So we're going to write down the lead. So this is eventually, this is eventually what our product side is going to be like after we interpret this word equation into a chemical equation. And this is what our reactant side is going to be. So we have the reactants on this side, and we have the products on this side. So now we have to check and see if this equation is balanced. So let's check and see, guys, if this equation is balanced, and then we can move on to another example. So if we look here, what we basically have, so let's erase all of that. so I can have some space. Okay, so eventually our final chemical equation after we convert the word equation is Pb, so we just write it neatly so we can balance NO3, and then we have 2 as a number of subscript, and then we have Z, NO3, and then we have 2 plus lead, Pb. That's too farther away, so we could do it here and there. So now the key is always the same thing as I said before. We need to write out all of our elements and compounds or polyatomic ions and see what their charges, the number of atoms are, sorry. So zinc has 1 atom on this side and lead has 1 atom. Okay, so don't confuse this two. This two only relates to nitrogen and oxygen. So lead has 1 atom, and then of course we have our nitrate, which has a charge of, has number of atoms of 2. So we can just write it like this if you prefer, or if you would like, we could break it down. So I think that's going to be easy. You could take it as a whole polyatomic ion if you'd prefer, because that's going to make it easy. But if you'd prefer, we could also break it down into separate elements. So we could do nitrogen, which basically has 2 atoms on the reactant side. This 2 also represents for nitrogen. And then oxygen, which basically has 3 times 2. So that's going to give you 6 on this side. Don't forget that there's a 3 here. So 6. Now let's break this side of the product. So zinc here has 1 atom. And then nitrogen again has 2, so it's pretty much the same. And then oxygen again on this side is a 3 times 2, which is going to give you a 6. So 3 times 2, which is equal to 6. And then we have our lead, which is Pb, and that's going to give us 1. It only has 1 atom. Okay, so I think we have everything covered. We have zinc, lead, we have nitrogen, and oxygen. So now this is pretty much what we have. So we have 1 atom of zinc on the reactant side, 1 atom of zinc on the product side, which is balanced, 1 atom of lead on the reactant side, 1 atom of lead on the product side, which is also balanced. We have 2 atoms of nitrogen on the reactant side, and then we have 2 atoms of nitrogen on the product side, which also makes it balanced. And we have 6 atoms of oxygen on the reactant side, 6 atoms of oxygen on the product side, which is balanced. So this equation does not need any balancing because it is already balanced, guys. Okay? So now let's look at another example of a word equation. So going back to our word equation question sheet. The second one says aluminum bromide reacts with chlorine to yield. Whenever you see the word yield, means it produces. So aluminum bromide reacts with chlorine to yield aluminum chloride and bromine. So we take it step by step and notch by notch. So that means if we look at what it says in the first part, it talks about aluminum. And we know that aluminum has a chemical equation of Al. So we write it down, but it says aluminum bromide, and we know bromide is Br, basically bromine from bromine. Now we just have to look at the ionic charges so we can determine the chemical formula. Now, if you guys remember what I said, when you go back to the chemical equation table, the polyatomic ion table, periodic table, and you're looking for aluminum, you see that aluminum has a charge of +3, and then of course bromine, which is bromide, in this case here on number 35, has a charge of minus or -1. So if aluminum has 3+ and then bromide has minus, if you exchange these charges, remember what you do for a chemical formula, you eventually get aluminum, which does not, has a charge of 1, which we don't write by convention, and bromine, which basically now has a charge of, which takes this ionic charge as a subscript to be 3. So aluminum bromide, the formula is BAlBr3. Now, the next thing, according to the word equation worksheet, it says that aluminum bromide reacts with chlorine to yield aluminum chloride. So chlorine, obviously, Cl is going to come with Cl, Cl2, chlorine, okay? Right, Cl2. We don't write it as Cl, but we write it always as Cl2. And it's yielding aluminum chloride. So aluminum chloride, again, we know that aluminum, so we get the chemical formula, has a charge of 3+. And we know that chlorine has a charge of minus from what we've seen before. So aluminum chloride, obviously, if you exchange these charges, they become the subscript values of these elements. So now it becomes Al, which takes the charge of -1. Remember how we said cations are always attracted towards the negative cathodes and anions are always attracted towards the positive cathode. So you can imagine this is pretty much what's going on. So it takes this -1 charge as 1, and then chlorine takes the 3. And so the chemical formula is AlCl3, so aluminum chloride. And they said it produces bromine or bromide. Let's see. Bromine. So bromine also, we write it, since it's a gas, we write it as Br2, just like chlorine. Now we need to balance these equations. So what we're going to do is the step we normally do. We write out all of the elements and the number of atoms they have. So aluminum has 1 atom. And we can see bromide or bromine has 3 atoms on the reactant side. Don't forget that this is the reactant side where these two things react, this compound and this element, and also this is the product side. Okay, so bromine has 3 atoms and chlorine on this side has 2. So now we write down what we have on the product sides. Aluminum has 1 atom, chlorine has 3 atoms, and then bromine has 2 atoms on this side. Sorry about that. I'll just write it again. Bromine. So we need to balance this, obviously, because we can see aluminum is balanced since it has 1 and it has 1 on the reactant and product. But bromine, for example, has 3 atoms on the reactant side, has 2. So we need to do something to this 2 so we can make it at least an even number. And we also need to do something to 3 so we take it to an even number. The key is always trying to get the numbers to even numbers so we can balance them. So the way we could balance this with even is if we multiply 3 by 2, that gives us 6, which means bromine would have this 2 atoms with it included now. So that means it has a total of 6 when you multiply the 2 by the subscript number of 3. And here we can multiply this bromine with 3 atoms. So that gives us 6 again. So that means bromine here would have 3. So you multiply it together, it gives you a 6. And now this is balanced for bromine on both sides, for both the reactants and product sides. Now we need to do something similar for chlorine. So chlorine has 2 on the reactant side, 2 atoms, and product 3. So what we could do is we multiply this by 2, so we get it to an even number, and that gives us 6. So if we put a 2 here, we now have aluminum becoming 2 as well. So we multiply by 2, so aluminum is now 2 atoms. And so chlorine, what we could do here is we multiply by 3, and we get a 6. So it becomes an even number, so we put a 3 here, and now it's 6 atoms. And here, don't forget that aluminum, now that its bromine has been, given this 2 atoms behind the formula, aluminum also becomes, I forgot to mention that time, becomes also 2 times 2. So that means it's now 2. So this equation is now balanced. We have 2, 6, 6, and we have the same thing here, 2, 6, 6. All right, guys, this is where I'm going to stop the video tutorial for chemistry today. I hope you found this useful on how to derive chemical formulas, how to balance chemical equations, and how to convert word equations into chemical equations. If you would like anything more in special or specific for chemistry, please let me know. Other than that, I will be following the lesson plan that I normally do with my students in chemistry, and I will just be doing video tutorials on them, and perhaps one of them will let you know. All right, guys, we're going to stop the video tutorial here. I wish you guys a great day, and please leave any comments or any suggestions you may have, and I'll see you guys next time. Take care, everyone.